we don't know anything about the quantum state, then measurement gives us very little information about it. But if we do know something, then we can attune our measurement process to obtain more. Let's see an example. Imagine that we know from a trusted source that our qubit state is either this vector or this vector. This we will call phi. Phi is the sum of 0 and 1. Remember, here we have vector 0, and the vertical vector is vector 1 on this graph. And this we will call psi, and psi is 1 divided by square root of 2, 1 minus 0. So we know that our quantum state is either this or this. Then measurement of this qubit in the standard basis will give us 0 additional information, because for both these states the probability of outcome 1 is the probability of outcome 0, they are equal, and it is 1/2. So if we obtain 1 as measurement outcome, it gives us nothing, because it has the same probability for both vector psi and phi, and the same is for 0. But we can choose another basis to obtain more information from this state. And I'm going to choose the basis which I will draw in green here. So this basis has also 2 vectors, of course, and the first vector we will call plus. It is this vector, and it's actually the same as vector phi. And vector minus, which is here, is this. This basis is called the Hadamard basis, in the name of French mathematician Jacques Hadamard. And now these 2 vectors are orthogonal, they are unitary, so they form the orthonormal basis, of course. And if we measure our system in this basis, then result plus will tell us that the system was and still is in the state phi, and minus outcome tells us that the system was in state psi before the measurement. So choosing the correct basis is crucially important for obtaining information from quantum system. Though we don't have a state-of-the-art quantum hardware here, we can still illustrate the measurement process. Remember I told you about the electromagnetic wave, that we can carry qubits coded by the polarization of photons. And the polarization is the direction of the wave oscillation, which is orthogonal to the direction of wave propagation. Fortunately, we have crystals which can detect and alter this polarization, this characteristic of a photon. And on molecular level, these crystals are organized like this. They contain dipoles, which are all oriented along one axis. And you see these little springs here on the picture. Actually, this picture is not exactly correct. There are no springs there on the molecular level, but the idea of a spring there exists. If we apply an electromagnetic field alternating electromagnetic field with the vector of oscillation parallel to this axis, then these charged particles, pluses and minuses, begin oscillate around the positions of the minimas of potential energy. And as you know, when charged particles oscillate, they produce waves. So this another wave, secondary wave, is depicted here in blue. And it's not hard to show that this wave, this secondary wave, will be shifted half of the period to the primary wave if this primary wave is, for example, sinusoidal. And here on the slide you can see the picture of the falling wave. Here we see this crystal from the side. So the falling wave falls into the crystal, it passes through, it is depicted in orange. And here we can see the secondary wave in blue, and of course it propagates in both directions. And this, which I drawn in green, it is a reflected wave, and this wave, which is orange, is primary, and blue is secondary. They are shifted half of the period, so they add up, resulting in no wave here. So the wave does not pass the crystal if it is oriented along this axis. On the contrary, if you have the wave polarized like this, then it does not cause oscillations of these charged particles, so it does not produce this secondary wave, and the wave easily passes the crystal. So this is why some materials are not transparent for some wavelength. If in the side of the material there is some charged particles which can oscillate with the frequency of this falling wave, then these charged particles produce secondary waves, and they self-destroy. This secondary wave self-destroy with the primary wave, so wave does not pass through this material and is fully reflected. And this is why all metals are not transparent for almost all frequencies of the electromagnetic waves because of free electrons there. And also this is why they are so shiny, because of these reflected waves here. And this is probably not a surprise to you. So if you have this axis, which allows the waves to pass, is called the optical axis of the crystal. So I draw here the optical axis. It is the axis for which all waves polarized along this axis, they are allowed to pass through the crystal. This axis is orthogonal, and all waves which are oriented like this, polarized like this, they don't pass the crystal. It is actually the line along which all the dipoles are oriented. And if we have a wave polarized like this, with some angle theta with the optical axis, then it is not probably a surprise to you that the wave passes through the crystal with probability cosine square theta, and it does not pass with probability sine square theta. So these crystals can perform for us measurement of qubits which are encoded by the photon's polarization. These crystals, linear polarizers, are easy to get. They are used in many modern devices. For example, the surfaces of almost all LCD screens have several polarizing films on them. But if you want to get something this clear and transparent, then you probably have to go to a shop where photographers buy their stuff. And the reason why photographers use these things, these linear polarizers, is this. Many surfaces, when they reflect the light, also polarize it. So you can either enhance this polarized light with linear polarizer or to reduce it. For example, if you want to take a picture of a blue sky, so you want to enhance the blue color of the sky, you can use this thing to enhance this blue color, because the light reflected from different layers of atmosphere is polarized. And if you want to take a picture of a shallow pond, of the bottom of a shallow pond, then you probably would have a problem with the rays of light which are reflected from the surface of the water, because they mix with the light which is reflected from the bottom of the pond, and they spoil the image. So with this polarizer, you can also restrict this reflection from the surface of the water, because it's slightly polarized. And if you have two of these things, then we can do even more, because you understand that the light which passes through the polarizer is polarized along its optical axis. So if we cross the optical axis of polarizers, then the light which came through the first polarizer is restricted by the second polarizer, like this. So now I hope you don't see me, and now you do. And aside of this useful application of hiding me from students, there are many more. Almost all transparent materials alter the light polarization. So if you put something transparent between these two crossed polarizers, then the light which came through this transparent material can now pass the second restricting polarizer, because its polarization slightly changed. And if we have some higher densities in this transparent material, then the light there is shifted, the light polarization is shifted more. So on these areas where we have higher densities, we will have more light, which is not restricted by the second polarizer. Here on this slide you can see the picture of ordinary glasses, which is put between two polarizers. So it is a picture in the polarized light. And you can see some tensions here. For example, on the place where glass is attached to the glasses rim, there are more light, because there are some tensions which the glass have in this glass has in this area. And thus we can analyze transparent materials, we can see the defects in them which we don't see in normal light. So we can now understand that these polarizers can perform the measurement process for us for the light polarization, and the choice of the basis is performed by rotation of the polarizer. So the choice of the basis is the rotation of polarizer, and the light which passes through polarizer is now polarized along its optical axis, and the light which is fully reflected is polarized perpendicular to its optical axis.